Yes.
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 Perfect.
Yes.
Okay, so welcome everyone. Thanks for joining the 10th edition of the NLP Breakfast, hosted by Feedly in our Redwood City office. My name is Edward. I am ML and NLP engineer at Feedly, and today we'll be discussing recursive routing networks in light of the recent publication by the Stanford NLP group. And as a first disclaimer, this is not a talk about recurrent neural network, but another form of modular learning through neural networks. And so the plan for this presentation is going to be first to state the motivation of the paper and remind what is natural language inference. Then we will talk about the newly introduced Stanford Corpus of Implicatives. And then we will go on introducing recursive routing networks and how this is a modular approach to the natural language inference problem. And then we'll discuss the results and some interpretation illustrations. So the first motivation of the recursive routing networks come from an observation that was made in an earlier publication by the same authors, which is an observation about the trade-off when in the learning process of neural networks, which is called the transfer interference trade-off. So what you see in this illustration is the evolution of the learning of the weights in a neural network on the left. And there are two phenomena that can appear when you train on a variety of samples. And especially if you look on the right, if you take two different samples, I and J, they can either try to optimize the learning parameters of the model in the same direction. And in this case, we say that there is a transfer, or they can have different affinity with the parameters of the model and therefore have gradients that are of negative dot product. And so intuitively what we like is transfer, but what we want to minimize is interference. And though we're used to stochastic optimization algorithms that take into account the history of the gradients, like the Adam optimizer or RSM prop optimizers that deal with the fact that gradients are going all over the place in the usual training, the observation of this paper is to, and the goal of recursive routing networks is to try to explicit this a bit more, which hopefully might also help for interpretability. And so recursive routing networks in this paper is going to be applied to the problem of natural language inference, which, as a reminder, is the task of determining whether a hypothesis is true, false, or undetermined given a premise. And if you look at the New York University multi-genre natural language inference corpus, it really looks like this. Like it's a data set of pairs of sentences with a label determining if the sentence on the left entails the sentence on the right or contradicts it, or if it's neutral. It has a lot of interesting applications, for example, question answering, but also summarization or multi-document summarization. Let's say you want to avoid repetition. If you have a sentence that entails another, you might not want to put both of these sentences in the summary. And also as well in the evaluation of machine learning, machine translation systems, you might not want to lose the entailment or contradiction patterns when you go from one language to another. So this paper introduces a new data set of natural language inference, which is exactly the same kind of structure as the one we've just seen, but it also has for each of the sentence in each of the pairs, it has something called a signature. And a signature is a twofold piece of metadata for each sentence that is determined by some central phrasal construction to the implicative. So for example, any sentence that has the word manage in it would have the signature plus and minus, whereas sentences having lacked foresight will have the signature minus and plus. So yeah, the signatures is composed of two parts, and it can either be it can either be free of these symbols, so either a plus or a minus or a zero. And the way we determine this signature is we take this phrasal construction and we put it in either a positive environment or a negative environment, and we try to see if in this environment the implicative entails this clause or contradicts it. So if you take manage and we try to put it in a positive environment, we have John managed to solve the problem, which entails that John solved the problem. Whereas in a negative environment, we have John didn't manage to solve the problem, which contradicts that it solved the problem. So the signature is as is. In the second example, lacked foresight, in a positive environment, John lacked foresight to solve the problem. This contradicts that John solved the problem, and vice versa in the negative environment. An example of how the symbol can be something different than plus and minus is hesitate. If you say John hesitated to talk to him, you don't know if John actually talked to him. So you have a zero here in the positive environment. Whereas in the negative environment, John didn't hesitate to talk to him, and still entails the thing. So it's not necessarily a binary asymmetric signature. And if you go even deeper, the paper talks about likelihoods of these phrasal constructions, because, for example, if you have the phrasal construction be able, I was able to speak, usually it means that you spoke. But if you take this sentence, I was able to speak but just didn't know what to say, it actually means that you didn't speak. So there is a 0.9 probability that in a positive environment, be able actually entails the implicative. And the last piece of information about signatures is that they are compositional, and you can nest them together. So in this example, you have fail to and take advantage, and you can apply the same reasoning and determine the new signature for the composed nested implicative. And if we take actually a step back and construct the tree of this signature, you can see that it's actually possible to do a simple operation to determine what is the eventual signature of the nested implicative. So this is what signatures are. And so the Stanford Corpus of Implicatives dataset is still a natural language inference dataset, but just with this additional metadata for each of these sentences. And this dataset comes into three variants. The disjoint dataset, which is that some implicatives will not be found in train and validation, but will only be present in the test set. So for example, any sentences containing be forced here will only be present in the test set and not in the train and validation. And there are 128 of them, for instance. And the mismatch one means that you're hiding some of the signatures. You're separating some of the signatures in between splits. So, for instance, this kind of signature whatever the construction here, this kind of signature will only be in the validation and not in the train and validation and not in the test. So all this introduction about this new dataset and the metadata that comes with this dataset echoes the first illustration that I presented early on, which is that we might want, for all of these examples for which we have different signatures, to have a differentiated kind of training. And so this is what recursive routing network are about. If you look at this overall illustration of how the network works, you have here the input matrix of your data, which instead of being fed to the same fully connected layer regardless of the sample, will have to go through something called the router, which is just a classifier that will tell you for each sample where to go to next. So you get your input, you classify it, and then it associates to you one of these fully connected layers. Your input goes through that, and actually after this step you can recurse again, so that's why it's called recursive routing networks. You can do the same process again and go through the router and go maybe to another fully connected layers, etc. And so what we have eventually achieved here is represented by this other picture, which is that for an input X, you can have different paths through all of these independently trained fully connected layers. So to explain a bit more this picture, so this is the forward pass in the training, and all of these squares here represent the same set of parameters, the same fully connected layer, but X goes through them in a different orders, and this order is determined by the router. And so this seems very elegant because, as we will see, it means that you're able to have different inputs goes in different paths of the model. And if we want to train that model with respect to each sample, we will have gradients that are separated with respect to the samples and the modules. The only thing that is tricky about this new architecture is that you not only have to train the modules themselves, but also you have to train the router, which is a much harder task that can be achieved, for instance, using reinforcement learning. But the router is essentially also usually a neural network kind of predicting function.
That's good. I'm not sure if this is true, but is this really just like an extreme form of attention? Like,
yeah, I think this is, if we should associate it to one of these, it's a form of attention, let's say. It's close to it. And so now to explain, to show in another representation of how the learning is differentiated for samples, I'd like to quote the paper to say these two quotes, which are that RNNs make global functional decisions at the module level, and that recursive routing networks explicitly make decisions to compress or orthogonalize knowledge between examples by deciding whether to share specific weights. So here you can see the different pathways taken by these two different examples, and this illustrates orthogonalized knowledge because they have very different pathways through the modules, and the weight sharing is very small. And if you look at this graph, which represents the evolution, the different values that can take the dot product between the gradients of these two samples, it actually looks like this, where we have very limited transfer and interference, because for these two samples they are they don't go through the same parameters of the models. Whereas here, compressed knowledge, they share a lot of similarity in the pathways that they take, and so you have high interference and high transfer. So now we're going to discuss how this can be applied in practice. And first, just as a reminder, we have a standard general architecture here, no novelty on this side, which is that what we want to do is we have a premise, a hypothesis, and we want to say whether it entails, contradicts, or is neutral here. So we have a classifier that takes the embedding of both sentences and does just this. And the first way you can apply recursive routing networks is by actually replacing any fully connected layer by the modules, the recursive modules that we've seen before. And so you can say, I'm going to replace just the classifier in the last layer of the model. I'm just going to replace the fully connected layers by this recursive module where where I have like B modules, so B independent sets of parameters, and we have D recursion steps. And so one feature of why it works and why it can be applied a bit everywhere still has to be that the input shape and the output shape are the same, because you are doing recursivity. And so the paper introduces various different uses throughout different models of it. And so, for instance, instead of now using the recursive module in the topmost layer, you can use it just at the embedding, just after the embedding. And so the classifier will still be a regular single fully connected layer, but now you're changing the way that you embed data, introducing this module in an earlier step in the algorithm. You can this is the continuous bag of word embedding here, that where they sum the embeddings of all words for the encoding of the sentence, but you can also use it in recurrent neural networks, and they explore two different fashions of using it, either before the encoding of the word before being inputted in the RNN cells, or between the time steps of the RNN cells. You can also apply it here. But so essentially, the routine modules can be applied anywhere where you have a fully connected layer and replace it. So now I'm gonna help you navigate through this table of results, which is quite big. What you have here is the configuration of the experiment. Here, this column is for the New York University multi-genre Natural Language Inference Dataset. And here is the Stanford Corpus of Implicatives Dataset with the different variants of it, the joint, disjoint, and mismatch. And so basically there are two models here, the continuous bag of words or the recurrent neural networks, which start with embeddings that are either, so pre-trained embeddings that are either from Glove or Elmo. And now their contribution is this column, which is where do we apply routing for each of these configuration. Do we apply routing at the topmost layer? Do we apply routing at the word projection level, so just after the word embedding? Or do we apply it like in between the recursive steps of the recurrent neural network? So you see how here all these recursive routing modules are orthogonal or complementary to recurrent neural networks. Recursive routing networks is not something that works on sequential data, essentially. It can work on any kind of data, and that's why it's really different from RNNs. And so if you look at these results, so for the biggest results here are for using Glove with a continuous bag of words and doing this word projection routing thing, plus a trick that I will explain that is the dispatcher trick. But we have to keep in mind that compared to the transformers, these results are still very far from the transformer in this model. But across this category of models, what these results show is that using routing can help improve the results for the natural language inference task. So I'm going to discuss just a bit this dispatching trick, which they talk about, and which is that actually when doing the routing and when classifying the data for it to choose one of the modules, you're leveraging the signatures, the metadata the dataset was constructed with. And for the New York University multi-genre natural language inference dataset, the metadata that is used is the genre of the sentence, which genre it belongs to. But the dispatcher trick says that since this data is not available, usually this metadata are not available at inference or test time, you can train beforehand, before everything happens, you can train a separate metadata predictor that will be used as an input to the router. So M is the meta information, and this is the router policy, and the router policy usually uses the embedding so far of the input, and also this meta information that you will have trained to learn before learning the full model. And now a nice visual interpretation of the results of routing. If you remember this illustration between of how the paths taken by the samples through the modules can overlap or be completely disjoint. Now these two heat maps show how these two dissimilarity metrics, show how similarity metrics actually show how the pathways can overlap or not. So if we take the multi-genre NLP dataset from NYU, what we have is that what we like to see is that on the diagonal we have a value of 2 here, which means that most samples share at least 2 of the 3 modules, go at least for 2 of the 3 modules, same modules, whereas for orthogonal genres, the pathways taken by the samples are not the same. And so what we want to say here is we might have achieved some modularity in the learning because samples having different metadata might have different pathways. And there's the same analysis done for the Stanford Corpus of Implicatives across signatures. So what we want to see here is still that the for signatures, like if you compare, so here you have a plus and a minus, and what we want is for signatures that are close to plus minus to have also some high kind of path similarity across the modules. So this was all for the presentation about recursive routing networks. In conclusion, they're a way to modularize learning and enforce how to counter effect the fact that different samples might have a contradictory impact on the learning of